All right, so welcome to day 2 of calculus. Um, so today's plan, of course, after we go over homework, we're going to continue our discussion of areas, and specifically, we're going to start looking at how to make the areas better, as we kind of saw last time. It seems like it's going to work a little bit better if we make more rectangles that are smaller. That will get us a better approximation. So we'll kind of go through that process, and we'll make it generic as we always do. But before we get there, I'm going to open it up to you guys. Are there any homework questions? Anybody get in there have any questions about what's going on with that homework?
Yes, I have a question about the homework.
Okay, go ahead, Bruno.
So it was question 3, and it says use the rules for sums of powers of integers to compute the sum.
Okay.
And it has the sigma notation with k equals 6 at the bottom and
Okay.
12 on top of sigma and
Okay.
k right next to it. 'Cause-
All right.
And I was trying to use I believe it was well, I got frustrated on this one because I was trying to use the first and the second sum formulas, but they didn't work out for me. So I don't know if there's a small detail that I'm missing that I'm understanding. So
Okay. We
I
can. I can definitely answer that for you. I also just want to mention real quick that Aries, I did see that you put in the chat you'd like to look at number 4, so I'll go ahead and put that on my list as well. Before I dive into answering your question, Bruno, let's just see if there are any others. I like making a list of all of them so I can just knock them out. So if anybody else has another one they'd like to see or anything else they're having issues with, let me know.
I have a question on one of them. It was like an interval of 0 to 5, and it said to divide it in 4 spots. So do you just approximately 4?
No, you don't have to do approximately 4. You can do it exactly. It's just not going to be whole numbers.
Okay.
But I'll talk about that as well. Let's see. Let me write that down here. All right. Anything else? Okay, well then let me go ahead and share my whiteboard, and we'll start talking about some of these questions. All right, so let me actually start with the one that Bruno was asking about, and let me make sure I got this right. It was the sum with k equals 6 to 12 of k. So is that right, Bruno? That's what I got from what you
yeah,
said.
that is
Okay.
correct.
Okay. So we want to try to get this sum. Now, we can brute force this if we wanted to. The fact that this is a k instead of an I, don't let that throw you. I think for you guys at this point in your math careers, you're probably good with the change of a letter doesn't really change anything. But if you think about what this is saying we want to start with 6. So we would plug in 6 to this and we would get 6. And we put a plus, and then our k would kick up to 7. Well, that gives us 7. Then it would go to 8. Then it would go to 9, 10, 11, and then lastly it would end up at 12, right? So this is what this actually means. This is the shorthand. This is laziness of mathematicians coming through, right? This is just the fast way of writing, well, we're adding the numbers 6 or 12. So if we just brute forced it, this is going to give us, let's see, 20, 40, 50, 63, I think is the answer to this, which is great if we just want to write them out. But I'd rather not do it this way, because what if these numbers get really big, right? Like what if this was k equals 6 to 120? I don't want to write out all the numbers from 6 to 120 and then add them all up. That's going to take forever. So that's why we're going to use those rules that we developed last time. When Bruno was reading what the instruction said, it said something about use the sum formulas or whatever, right? So this is the one we're going to use. We're going to use the fact that if we've got a sum from 1 to n of I, this gives us n times n plus 1 over 2. So this is the really generic. I've got it as an I instead of a K, but big deal, right? Just different letter. But this is just making it so that we can go to any number. So for example, like this one with the 12, if we were to have it as I equals 1 to 12, this would be 12 times 12 plus 1 over 2, or 78, because that's 12 times 13 divided by 2. Okay, however, notice that that does not equal 63, right? We have a number that's too big. So why is it too big? Why didn't this formula actually work for us? Does anybody see why? Okay, so Juan just said subtract 1 to 5, right? And Susanna just said left-hand sums on the increasing graph. It's actually not the left or the right, but it is the fact that this sum started with 1. And our sum doesn't start at 1, right? This one right here, the sum from 1 to 12 would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus, I'm already tired of writing them all out, but I think I actually made that a 111. Sorry about that. All right, so this is actually what we just calculated. But the problem is we don't want those guys. Those weren't part of our original sum. So we do have to subtract those off. So like Juan said, we need to subtract out the 1 to 5. So there is a sum rule. I don't remember if I mentioned this one or not. But basically what this says is that if you've got a sum from 1 to n, you can actually split it however you want. So like we could take this guy that's from 1 to 12, and that's actually going to be the same as the sum from 1 to 5 plus the sum from 6 to 12. Because we're still catching all the same numbers. We've just split it anywhere we want. So this is totally legal. It doesn't matter where your sum is. You can split it anywhere you want. So basically what we need to do is subtract those off. So the sum we're looking for, which was from 6 to 12, we can find that by taking the sum from 1 to 12 and subtracting off the sum from 1 to 5. All right, well, we already have that number for 1 to 12. That's 78. So now let's take away the sum for the 1 to 5. Well, we use the same formula. I'll run it up here. Go from 1 to 5. This is now going to be 5 times 5 plus 6. Whoops. How about 5 plus 1? My brain is one step ahead. Over 2. 5 plus 1, of course, is 6. 6 times 5 is 30, divided by 2, and that's 15. All right, so our sum then is actually equal to 78 minus 15, which is that amazing 63 that we found earlier. So this stuff at the bottom, coupled with the two actual sums from 1 to whatever, that's the using the sum formulas to find this. And for this specific one, we definitely spent more time using the sum formulas than just adding them directly. But this isn't where you would use this, right? Where you would use this would be if you are doing something like, let me do this over here in blue, like if you're going to do what's the sum from 72, let's go, I equals 72 to 249 of I. That one you don't want to write out. Oh, good Lord, you don't want to write that one out. And then add individually. That would take forever. So instead, let me show you how fast that is if we use the sum formulas. Okay, so if we're going to do the sum from 72 to 249, that's going to be the sum from 1 to 249 minus the sum from 1 to 71, right? Because we got to subtract off the first 71 of them. So this is 249 times 250 divided by 2 minus 71 times 72 over 2. So that's 249 times 125 minus 71 times 36. And you can punch that into your calculator and get an answer like that. So, excuse me, this is the reason why we care about the sum formulas, is for problems like this guy. Because, you know, I keep talking about how mathematicians are lazy. Aren't we all actually lazy? I think everybody wants to do as little work as possible. And that's not a judgment. That's actually a universal thing. I also teach physics. I don't know if you guys know this, but everything in physics, everything in the universe is about minimizing energy. Everything. So why are we any different, right? We're part of the universe. Well, we're gonna want to save ourselves some time. This is a great way of doing it. So, because I know everybody desperately wants to know what that answer is. It's 28,560. Right? Anyway, so is that better for this one, Bruno? Have I beaten this one to death enough for you?
No, it makes sense because I was having a lot of trouble with that one.
Okay, so thanks for asking that, though. I'm glad I was able to clear up that question. All right. So let's address the question from Alexi real quick, and then we'll get to the number 4. So I'm going to go ahead and clear this whiteboard. Okay, so Alexi, you had something that was like you were doing some graph, and you were going from 0 to 5, if I remember correctly, and it said to split it into 4 pieces. Is that right? So what we want to do is we want to figure out where are those intervals. So we want to remember what we're doing is we're partitioning. So we're just taking this interval and we're breaking it into chunks, but we're going to do a regular partition, meaning that all of them have the same width. So if you want to figure out what the width of those partitions is, all you got to do is think about how long is this interval first, right? So if we go from 0 to 5, clearly that's length 5. If you don't start at 0 and you start somewhere else, all you got to do is subtract the 2 numbers, right? Take whatever the right one is, subtract the left one, and that gets you your length. So this is our total length. But we want to split it into 4. So if we're going to split that into 4, what mathematical operation do you do?
Divide.
Yeah, you just divide. So if the total length is 5, then the little interval length, it's going to be 5 divided by 4. And so you can either do that as a fraction, or you can do it as a decimal. Doesn't really matter. They're both equivalent. So what that would look like then, if this is our interval from 0 to 5, where when we split it into 4, right, there are 4 chunks. This first one's going to be 1.25. The next one's going to be 2.5, then 3.75. Or if you want, you can go with their fraction equivalents, 5/4, 5/2, 15/4, right? So there you go. So it doesn't actually matter what your interval length is or your n. You always just take the total interval length and then divide it by that n. Okay, so don't let it freak you out if you don't get integers. I'll just tell you that the only reason we got integers the first time was because I intentionally set it up so that it was nice because it was the first example. You will never, ever, if you actually are doing this in the quote unquote real world, if you partition, you don't get integers. The real world's not nice like that. So it's totally fine to get things that are decimals or fractions, right? I mean, it could even be things like they're fractions of pi, right? Or e/6, or whatever. So anyway, same story. We're still taking that entire length and splitting it equally. That just means divide by n. In fact, if we wanted to make this nice and generic, we could say, okay, let's call these guys A to B, and we're going to do n intervals. Then the length of each of the smaller intervals, what's it going to look like? Well, we need the total length of this interval, which is the difference in those two. And then we divide by how many intervals we have. So the interval length, the small little intervals, are going to be b minus a over n. So hey, check that out. We just figured it out for any problem. No, nothing? No cheers? No. But this is how mathematicians think. It's like, well, instead of doing the same thing over and over and over and over and over, find the interval length, divide by n, let's just do it once. You do it once, you get one formula, and now it's just a matter of plugging in the correct numbers when you've got your specific problem. All right, so is that better, Lexi? Yeah, all right, cool. Thanks for the thumbs up. All right, so then lastly, let's go back and look at number 4 from 1.1. So Eric has asked about that one. So I'm going to go ahead and jump over to our Canvas page, and we'll go find that. All right, so 1.1, number 4. All right, let's take a look at number 4. All right, so for number 4, now your number 4 might look a little bit different. You might have different values, but it's really kind of the same idea here. Excuse me. But what we know is that we've got these two terms. There's a sequence of A's, so A1, A2, A3, A4, so on. And there's also a set of B's, B1, B2, B3, so on down the line. But if we add up these 87 A terms, we get -1. And if you add up the 87 B terms, you get 3. So the question is, what do we get if we add up the first 87 terms of -12 AI plus 7 BI? All right. So let me go back to the whiteboard. So let me clear this and let's see if we can answer that. So again, the pertinent information, we're looking for the sum of minus 12 AI plus 7 BI. And we were told the sum of the A's was -1 and the sum of the B's was 3. All right, well, this is where we're going to use our rules for sums. So we had a whole bunch of them, but the two that are important here, the first one is we've got addition of functions, addition of terms. So does anybody remember what that lets us do, what the rules of sums let us do there? I'm not looking for substitution, Susanna, although maybe that's what maybe substitution is in your mind different than what I think. Okay, so Alexis says distribute the summation. I definitely like that better. What this says, since we're adding two things, we can actually split it into two sums that are being added. So we can actually pass that sum through to each of those pieces. If it's being added, subtracted, you can definitely do this. It basically comes from the associative and commutative properties of addition, if you want to be really technical. Okay, and then what can we do with these constants that are on the inside, these constant multiples? Do you remember what sums allow us to do there? Cool, thanks, Alexi. Exactly, move them out front. We can factor them out. So this would look like minus 12 times the sum of the AIs plus 7 times the sum of the BIs. So all of this, these two steps, we're using associative and commutative properties, and then the distributive property. So all those things you learned way back when, the basic properties of numbers, are being applied here just in a fast way, right? In a fast, lazy way. But now that we're here, we're ready to go, because this sum, this one right here, we know its value. It's equal to -1, right? The sum of all those A terms was -1. We also know the sum of all those B terms is equal to 3. So we can substitute those numbers in, get 12 plus 21, which is 33. So in a situation like this, we don't even have to know what the individual terms are, right? Like I have no idea what A1, A2, A3, B1, B3, B87, I don't know any of these things. But because I know what their sums are, and because I know the properties of the sum, I can get to these answers. Right? So like I said, your problem might look a little bit different, right? It might have different values, but it's going to be the same process. Split it apart if you've got addition or subtraction, pull any constant multiples out front, and then you can substitute back in for your original sums. All right, and I think that was Aris who asked about this. Is that good, Aris? All right, cool. All righty, so hopefully this sum stuff is starting to come back. If it's been a while since you've seen it, if you've never seen it, hopefully it's making a little bit of sense. But if you're still having trouble with it, come talk to me during an office hour or something. Send me an email or a message so that we can chat, because I want to make sure that you guys are good with it. We are definitely going to be seeing more of it today, because where we're going is just more addition, right? So that's where we go. All right, so are we good for homework? Are we ready to move on? All right, awesome. Real quick, while we're talking about homework, just to give you one more thing, because I did get a message from someone about this. The homeworks are set up so that when you do the problem, you do only get one chance in terms of that specific problem, right? So if you get it right, cool. If you get it wrong, you can do, there's a little thing there that says like, try another, or try a similar problem or something like that. If you click on that, it brings you another problem that looks very much the same. Like take that one we just did. Let's say we had gotten that wrong. You hit try another problem. It's going to give you another sum, but it's going to change the numbers, right? So it's going to say the sum of the A's is 4 and the sum of the B's is -2, all right? But it's really the same process. So you can go through that problem and again, get it right, great, get it wrong, hit, try another problem. And you can do that. I just saw that it was set so that you got 10 attempts on any one problem. So you can do 10 individual ones. So you got plenty of chances to get it right. But just realize that you have just the one chance per problem to put in an answer. So hopefully that makes sense. If not, come chat with me and I'll try to explain it in a better way. All right, well, I'm going to hop up to the whiteboard then. So give me 1 second and I will see you in just a moment. All right, so sorry about my pen there. So let's think about where we were last time and what we were talking about. Remember what our goal is. Our goal is to answer that area question, right? Given a weird shaped area, how do we actually determine the size of it, right? And what we came down to was, well, let's use rectangles. So the example we were looking at last time, if you guys remember, was just x squared. And we were looking at x squared between, I believe, 0 and 4. So it looked something like this. So here was 4, 0. And we were trying to find the area of this region in here. And so what we saw is that we could split it into, we could partition the interval 0 to 4 so that we could create some rectangles. We could calculate the areas of those rectangles and use that as an approximation, right? And we saw that we were getting a better approximation as we increased the number of rectangles. And we saw that we could use the right endpoints, we could use the left endpoints. I didn't mention this last time, but you could use the midpoints. You could actually use any point in any of the intervals. It's just we try to be regular. We try to do things systematically, just because it's a lot easier if you just go, okay, always use the right endpoint or always use the midpoint instead of, oh, in the first interval, I'll use the midpoint. And then the next one, I'll use the left endpoint. And then the next one, I'll use the right. Right? Mathematicians don't like that. We like systematic. We like, here is the recipe, do the recipe, right? So, but regardless, what we're going to do is we're going to split this thing into a bunch of intervals, and then we want to make those intervals get bigger, or I mean, get more of them, right? Okay, so I want to do this in such a way that we can actually apply math to it. Okay, so let's kind of generalize what we were doing. So first of all, let's write down what the process is, right? We had to partition the interval. So then we had to find the widths of the rectangles. Or actually, we'll just say we had to find the area of the rectangles. And then we had to add them up. Right? Like if you were going to give somebody the process, what's the recipe for doing this? This is what you'd say. Partition that interval, divide it up. Then find the area of all those rectangles, and then add them up. All right, so if that's the process, let's break that process down mathematically. And let's see if we can do it a little bit generically. Okay, but I'm going to kind of work backwards. So let's just think about what we're going to do. At the end, we're going to add up areas, right? So we're going to have area 1 plus area 2 plus area 3 plus a whole bunch of other areas. And then we're going to end with area n, right? So the last one, area number n. So like I think the furthest we got was where we split it into 8 intervals. So it would be area 1, area 2, area 3, all the way out to area 8. Okay, so we'll just let n be the number of areas that we've got. All right, well, a mathematician looks at this and goes, since I'm adding up a bunch of things that are exactly the same, let's make this a sum. Let's make that a sum formula. Because what we're doing is we're adding up areas. We're going to call them area I. And those i's are going to range from 1 up to n, because there are n of them. Okay, so that's the add up the areas part. So now let's think about how we find the area of those rectangles. So I'm going to come back to this picture and I'm just going to draw one of the rectangles that we calculated. So let's say it's this guy. All right. So this is going to be one of those areas. All right. This is area I, or one of the I. All right. So how do you get area of a rectangle? What do you need to know? All right. You definitely need to know width. What else do you need to know?
Your base times height.
So we need the width and we need the height. So we need base times height. Okay, so if I were to now start breaking this down again, this is going to say then we're going to have our sum 1 to n. But now what we need are the height times the width, right? Base times height. All right, so the way that we got the height of this rectangle was by plugging in a number. Hopefully you remember that. That was the whole left endpoint, right endpoint. You plug in some number in here into the function, and it gives you an approximate height, or it gives you a height for that rectangle, which is going to give us a rectangle that approximates the actual area. Okay, so that height then, I'm just going to call this f of x sub I. And all x sub I is it's some number that's in the ith interval. Okay, so x sub I is a value in interval number I. All right, so x sub 1 would be something in the first interval that we create. X sub 2 is something in the second interval. X sub 3 is something in the third interval, and so on down the line. Okay, but we just plug it into our function to get our height. And then how do we get our width?
From your f of x.
And that actually doesn't come from the f of x. The f of x gives us the height. Think back to that question that, that I think it was Alexi asked me. Right? So there you go. Alexis just put in there. How about the b minus a over n? Erez mentioned delta x. We could call it delta x sub I. And actually, that's probably a good way if we want to make it just for a general partition. If this is any old partition, delta x sub I is just the width of interval number I. So let me actually put that here with this. X sub I is the value in interval number I. delta xi is the width of interval I. Right, the width comes from our interval length. The height comes from our function. But if we made this regular, we made it a regular partition, we saw that we can get those widths by doing the b minus a divided by n. So let me go ahead and put that here. If I change this to a regular partition, we have for 1 over n, f of x of I times b minus a over n. So the difference here is that this is for a regular partition. This other one is for a general partition. So if you don't want to make it so that the widths are all the same, that's fine. Just make sure you multiply the correct width every time. But it's going to be easier for us if we make them all the same, if we make them regular, and then we've got this formula right there. Well, believe it or not, we have now set ourselves up to do any shape like this. All you need to know is what the function is that's giving us the height of these rectangles. I don't know about you, but I love this. Not this this specific thing, but I love this generally. I love doing it one time. If there's ever a situation where I can do the math one time and get the structure one time, so I just plug in my specific thing into this formula, I love that. I love getting all the work out of the way at the beginning and never having to worry about it again. Right? We don't have to think about partitions anymore. As soon as we go, oh, it's a regular partition, cool, with b minus a over n, multiply it by the heights. Done. Right? We don't have to think anymore. Now we can just go into what I call monkey math, right? Math that you can train monkeys to do because you don't have to think. Don't take offense to that. If you're having trouble with this, you go, oh my God, he thinks I'm not as smart as a monkey. No, it's just I'm a child. I really am. I'm a child in an adult's body. And I think about everything kind of in a weird, jokey way. And so that's, to me, it's monkey math. I actually picture the little like monkey, the monkey grinder. I know that playing the little music, and it's like The Simpsons. You know how Sideshow, I think it's Sideshow Mel has a little monkey that's with him. I picture that monkey every time I get into this kind of math because, like I said, I'm a child. Anyway, I digress. So let's actually apply this to this function, to x squared from 0 to 4, and let's make n really big. Let's make n big so that we can get an idea of what kind of area this is starting to approach. All right. Before we do that, though, I just want to mention that this process to actually find areas, and I didn't mention this before, so I should probably, this is the CYA, right? Cover your ass statement. For this to work, f of x must be positive. It's got to be above the x-axis. If your function is below the x-axis, you're not actually calculating the area. You're going to get the negatives of the area. All right, so this is only true to calculate area. F of x must be positive. We're also assuming that our function is continuous. Turns out it doesn't necessarily have to be continuous. There's some discontinuities where we can still do this process. But for sure, if f of x is continuous, you can do this. But make sure you realize that if f of x is not positive, you're not finding area. We'll talk about that a little bit more in detail after we do this. All right, so let's see if we can generalize f of x equals x squared from 0 to 4. All right, so let's see if we can get our heights and our widths and calculate this guy. All right, so first of all, first thing I'm going to pick is how we're going to choose our points in the interval to get our heights. Let's use right endpoints. Okay, just because it doesn't really matter. Let's just pick right endpoints. That way it's going to be always the same. All right, so we're going to use right endpoints. All right, so let's start setting this up the way we need to do. So think about what we need to do. We need to find the areas of the rectangles. So here, let's start with the width, right? The delta x. It's going to be b minus a divided by n. So that's going to be 4 minus 0 divided by n. All right, we're going from 0 to 4. 4 minus 0 divided by n, which is 4 over n. So the widths of each of these intervals is just going to be 4 divided by however many we have. And again, this kind of comes back to like that question that Alexi had, right? What do you do when you have a number of intervals so it doesn't divide it evenly? Yeah, just do the division. Doesn't really matter. All right, so there's our widths. Okay, so then we have to get our heights. Now, if we think about the heights, let's go back to kind of the picture of the partition. There's 4, here's 0. Let's think about what these different points are going to have as their values. All right, well, how wide is this first interval? What's the width of this interval? All right, so it's not 1, but it is 4 over n. Remember what we just calculated? This guy delta x? That was the width of each of these intervals if we're nice and regular. So that means we have to go from 0 to 4 over n. Okay, so this guy is 4 over n. If I want to get the next place where I cut this, I have to add another 4 over n. So I'm going to write this as 2 times 4 over n. Let me write it up here. And yes, that is 8 over n, but I just want to write it as 2 times 4 over n. So you realize that we're doing 4 over n plus 4 over n. How about the next one? How would you get its value? All right, cool. Thanks for that, Susanna. It's going to be 3 times 4 over n, because we're just adding another width of 4 over n. The one after that is going to be 4 times 4 over n, and so on down the line. Okay, so those are the numbers that we're going to be plugging into our function to get the height. And do 4 over n squared. Then we're going to take 2 times 4 over n squared, 3 times 4 over n squared, 4 times 4 over n squared, and so on. Okay, so that tells me then that my x sub I, the number that I'm choosing to plug in, is going to be 4 over n times I. And at this point, you might go, whoa, 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 whoa. Where'd that I come from? Well, think about what we're doing. Remember, each time here, this 4 over n is being multiplied by a number. And that number is the interval that we're in. 1 times 4 over n is the right side of the first interval. 2 times 4 over n is the right side of the second interval. This is the right side of the third interval. This is the right side of the fourth interval. So for the right side of the ith interval, multiply by I. Okay, so this is why I actually wanted to use right endpoints, because it's super easy to find these values. All you do is you take the width of each interval and you multiply by I, because you just keep adding that every time. So you may remember before I said you can pick any point you want in there, but it's nice to be systematic. Now maybe you're seeing why it's nice to be systematic. Because now ask me an interval. Ask me one, to tell you which point I'm going to use in any of these intervals. It's super easy. You say, hey, Bruce, I want you to do the 10th interval. Okay, I'll do 4 over n times 10, plug that into my function. What about the 30th interval? 4 over n times 30, plug that into my function. What about the millionth interval? 4 over n times a million, plug that into my function. Right? I don't have to think anymore. I'm just spouting out the same thing every time. Okay, so let's put this into the sum formula. Let's put this into here. So if we want to find the sum for any n for this function, this is what it's going to look like. I'll leave this just so we can look at it again. The area is going to be approximately equal to, this is an approximation, right? But it's going to be f of, the sum from 1 to n of f of 4 over n times I times 4 over n. So that's the sum from 1 over n of 1 to n of 4 over n I squared times 4 over n. So that 4 over n times I got squared because my function was x squared. All right, well, if I multiply through distribute kind of stuff, I'm going to get the sum from 1 to n of 64 over n cubed times I squared. So squaring the 4 over n, that gives me 16 over n squared, times another 4 over n gives me 64 over n cubed. All right. So now we're going to make use of the sum formulas. So notice that 64, obviously, that's a constant. I can pull that out front. N cubed is also constant in terms of the sum. The sum, the variable is I. So I can pull that n cubed out as well. So I get 64 over n cubed times the sum of the I squareds. And we have a formula for that. I showed that to you last time, or reminded you about it last time. So let's replace that. So this is 64 over n cubed times n plus 1 times 2n plus 1 over 6. And I can simplify that down just a little bit more. Right, the 64 and the 6 reduce. I can divide those both by 2. I get 32 on top and 3 on the bottom. One of the n's cancels here, the n and the n cubed. So I'm left with n plus 1 times 2n plus 1 over 3n squared. All right. So what? Well, check this out. This is actually the approximate area. This is the approximation that we get using n subdivisions. So now if you were to say, all right, hey, let's take that interval from 0 to 4 and split it into 100 chunks, I plug 100 in here, and that's the area that I would get. Break it into a million chunks. Okay, I'll plug in a million. And that's the approximation I'm going to get. We basically now have a formula that says, what is the approximate area if I tell you how many intervals to break it into? So let me just show you, let's plug in a number. And we're going to start with a number that we already know what the actual value was. Let's try n equals 4. If n is equal to 4, then we know that our area is approximately equal to 32 times 5 times 9 divided by 3 times 16. I just plugged in a 4 everywhere there was an n. Well, let's simplify this thing down, or let's calculate it. So 32 divided by 16 is 2. 3 goes into 9 3 times, so I get 2 times 5 times 3, which is 30. So when n is equal to 4, the right endpoints give us an area of 30. And if you go back and you look at your notes from last time, we calculated this. And I know what you're thinking. Right, we calculated that, but it was super easy. We didn't have to do anything, all this nonsense. And you're right, it was super easy. But now, what if we wanted to split this into 10? So I'm going to make 10 intervals because it should give me a better approximation. Okay, well, go ahead. Do it the old-fashioned way. Split it up, find all the different heights, multiply, find the areas, and add them up. Guarantee you I'm going to beat you because I've got a formula. I just have to plug in 10. So I'm going to get 32 times 11 times 21 over 3 times 100. And now all I got to do is do this on my calculator. So let's see what that is, because it should be a better approximation for the actual area. So let's see, I get 32 times 11 times 21 divided by 300. And I get 24.64. So this should be a better approximation for that area because we're using more intervals. The difference between the rectangle areas and the actual area is getting smaller. All right, well, that's great. That's if we did 10. Let's do 100. Let's break it into a bunch of little pieces. Okay, so now our area is going to be around 32 times 101 times 201 divided by 3 times 100 squared. And I apologize, I'm running out of space around the board. But let's see what that number gives us. So we got 32 times 101 times 201. All right, I get 21.6544. All right, so take a look at these numbers. So we started with 30. We got 24.64. Now we're at 21.6544. And as n is increasing, we're getting a better approximation. All right, but now here comes the mathematician. The mathematician says, you know how we can make this really good? Let's let n go to infinity. Let's 100, screw that. Let's go big. Not a million, not a billion, not a trillion. No. Let it go towards infinity. So the next big leap was to say, let's take a limit. as n goes to infinity. Because as we get closer and closer and closer to infinity, this area, this approximate area, gets closer to the actual area. All right, so let's remember how we do infinite limits. When you've got a fraction like this, what we want to do is figure out the degree on top and the degree on the bottom. So let's start by multiplying out. Let's distribute out on top. So if I were to FOIL that, multiply by 32, I'm going to get 64n squared plus 96n plus 32 over 3n squared. So that was just some algebra real quick. So do you remember what we do now? You look at the degrees and you notice that they're both the same, right? They're both squares. So what's the fast way of calculating the limit? All right, good. So Alexi just put in the chat that when the degrees are the same, you just use the coefficients. So you look at the degrees, the highest degree terms, and you just take their coefficients. So in this case, that's 64 and 3. All right, so if we were to allow this process to just go and do more and more and more and more, we get 64 thirds. All right, well, 64 thirds as a decimal. Let's see, that's 21 and a third. So 21.3333333333 forever. And notice that we're getting pretty close already. By doing 100 terms, we're within 0.3 of the actual area. But here's the beautiful thing. This 64 thirds, this is the actual area. It's not an approximation anymore. By taking this and going towards infinity, we're actually getting the actual value. All right, so this is how mathematicians answered that area question. They went, well, let's just split it into a bunch of things, make those things really, really small, add them all up. All right. This kind of trick was done in lots of places for lots of different things. And in fact, this was known before calculus was even invented. You guys know about Archimedes. I'm sure at least have heard of Archimedes. Ancient Greek, lived way back when, I think. I forget which city-state, but anyway, he used to do this kind of thing. He didn't call it calculus, but he was one of the first to actually investigate this idea of infinite processes. And that's what calculus is all about. Calculus is all about this limit idea. And so once mathematicians were able to do that, now we were able to create calculus and answer these awesome questions. All right, so yay, we just found the area under the curve x squared from 0 to 4. All right, let me give you some terminology. Let me kind of wrap all this stuff together, and then we'll start talking about, but there's got to be a faster way, right? There is. There's definitely a faster way. But here's what's going on. We make this nice and generic and, you know, put this, wrap it all up, tie it with a bow, as they say. Here's what's going on. All right, if f of x is greater than or equal to 0 and continuous, we are definitely making that assumption right now, then the area under the curve over the interval a to b it's going to equal the limit as n goes to infinity of the sum from 1 to n of f of b minus a over n times I times b minus a over n. So this is the one that you want to put a box around. Right, we put the box around it, reminding us to pay attention to this one. But there you go. This is how you do this for any function. It doesn't matter. Any interval, it doesn't matter. All you need to know to do this, if you look at this, there are only 3 things you need to know. You need to know B and A, right? You need to know those 2 numbers so that you can figure out the widths. And you need to know F. That's it. Because the n eventually goes away when we take the limit. All we need to set this thing up is the interval and the function. It's easy for me to say, oh, that's all you need to know, because then we have to do all the work on it. But we don't have to think anymore, right? We're to the point where it's monkey math. We've got the recipe, plug it in and go. We did all of the thinking work one time. Got us to where we can just plug stuff in. So let's try another function. I'll try to make sure that we don't get too crazy in terms of the functions, because we don't know some rules for lots of things. But how about we try this one? Let's find the area under x cubed minus 1 on the interval 2 to 5. All right, so another function, it's a polynomial. You'd all graph it, right? You all know what x cubed minus 1 looks like, or could get its graph. So let's just think about it first. Is it continuous? Hopefully all your heads are bobbing up and down. Yep, it is continuous because it's a polynomial. Polynomials are nice. We can do whatever we want with them. All right, so it's continuous. And we've got ourselves an interval 2 to 5. So let's set this sucker up. All right, so we need b minus a over n. Well, b minus a over n is going to be 5 minus 2 over n, or 3 over n. So there's our widths. So if we go to our formula then, we know that that area, it's going to equal the limit as n goes to infinity of the sum from 1 to n. It always starts like that. But now let's plug this stuff into our function. So we're going to do 3 over n times I cubed minus 1 times 3 over n. So take a second and compare that, what I've got in black, to our formula that's in the box. So you can see where everything comes from, right? The limit in the sum is there because it's always a limit in a sum. This is 3 over n I cubed minus 1 because that's the function. The function was x cubed minus 1, right? X cubed minus 1. And what we're plugging in for x is that width, 3 over n, times I. All right, so that's the stuff in the brackets. That was our function, so that's the height of the individual rectangles. And then we multiply by the width, 3 over n. So any questions on the setup? Are you all good with how I have what's in black? Give me a thumbs up if you're good. You guys know about the thumbs up? If you don't, it's under the, oh yeah, everybody's throwing them at me. Okay, that's usually how I can tell if we're good. You can just give me the thumbs up and I'll assume we're good. All right, thanks guys. Oh man, I just got an overwhelming, like 90% of you just threw a thumbs up. I like it. Okay, so now let's do the math. Well, here we go. Let's do this thing. So we need to cube this, distribute the 3 over n, blah, blah, blah. So we're going to get the limit as n goes to infinity of the sum from 1 to n of, all right, distributing this gives me 27 I cubed over n cubed. Now when I pass that 3 over n in, the limit as n goes to infinity of the sum from 1 to n of 81 I cubed over n to the 4th minus 3 over n. All right, let's use our sum rules. So we're going to get 81 over n to the 4th times the sum of I cubed minus the sum of 3 over n. So I did two things there. The first was I split it into two sums because of the subtraction. And the second was I pulled out all that stuff that doesn't have I in front of that first sum. And so now I can replace that sum of I cubed with the formula. All right, well, that one was n times n plus 1 over 2 squared. Go back and look at your notes and you'll see that the sum of I cubes gives you this. The other one, we're going to get minus 3 over n times n. That was the constant sum. If you add a constant, the sum of a constant, it's just that constant times n. All right, so let's simplify this a little bit before we take the limit. So we've got our area, the limit as n goes to infinity of, we're going to get 81 times n plus 1 squared over 2n squared. I get an n squared on top, that cancels with my n to the 4th on the bottom. And then we get minus 3. All right, so we take that limit. This is going to give us 81 over 2. If you distribute out, look at the leading coefficients, you'll see that they're both degree 2. So those coefficients are 81 over 2 minus 3, which is 75 halves. There you go. That's the area under that curve between 2 and 5. 37.5. Okay, this was huge because now all of a sudden you have any shape that looks like this, as long as you can describe this with a function, we have a process. Yay. Well, it turns out that if you want to go to shapes that look like this, we're going to be able to apply the same thing as long as we can describe the top and the bottom as two separate functions. You can do the same thing if it's turned sideways. They're just functions of y. Like, this was awesome. This was huge. Because now the area problem is answered. And in terms of applications, there are tons of applications where we need to know the areas of shapes. And out in the real world, shapes are not always nice. They're not rectangles. They're not triangles, right? Okay, so there you go. This is the process every time. Now, what we're doing here is called, or these sums that we're taking, they have a name, and they're called Riemann sums. I'm mostly just giving you this name so that when you run into it, you know what that means. Named after a German mathematician. So it's Riemann. All right, so that's a Riemann sum, and the Riemann sum is that sum from 1 to n of the f of xi times delta xi. So if you ever read anything and it says the Riemann sum, blah, 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 okay, it's that we're finding the area of this thing. So that's called a Riemann sum. So in order to tell somebody how to find the area, you're basically saying, well, find the limit as n goes to infinity of the Riemann sum. But we don't want to say that every time. We don't want to write that every time. So we do have a notation for what we're doing, other than that whole limit as n goes to infinity of the Riemann sum stuff. And so this is the notation we use. We call it a definite integral. And this is what we're going to write. You may remember from last quarter the integral symbol. You guys remember seeing that before? What did that mean? What did we see that? What was the context of it last quarter? It's the very last thing we did.
Integrate the function or take the antiderivative.
So it was antiderivative. Good. So it was the antiderivative. It told us, hey, find a function whose derivative is what we were just given, right? But when we make it a definite integral, we actually put numbers on here. We call them bounds of integration, but we're going to put an a and a b. These a and b, those were the interval chunks. All right, and then we're going to have in here f of x dx. So the way to read this, is this is our function. The technical name for that is the integrand. This is the last time first and last time I'm going to say that in this class, but this is the integrand. All right, the dx, the name for this is, it's a differential. Hopefully you remember those from differential calculus, right? It basically is just telling you what we're differentiating with respect to. In this case, it's what we're integrating with respect to. Again, that's not new from what you saw before, but the a and the b, these are the bounds of integration. And that's what's new. So as soon as we throw on bounds, it doesn't mean antiderivative anymore. As soon as we throw on bounds, this is the area under f of x on the region or on the interval a to b. And I do want to point out again that when I say area under f of x, that's if f of x is positive and it's continuous. We're going to see that actually this isn't always area under the curve. It's all kinds of other stuff. All right, so that problem that we just did with the area under x cubed minus 1, we could actually write that with a definite integral, and it would look like this. We're going from 2 to 5. That was the interval. Our function was x cubed minus 1 dx. And that's what we found was equal to 75 halves. So this is the notation we're going to use. That's how you're going to know what we're doing. Remember the very first one we did? We were going from 0 to 4, and we were looking at the function x squared. Right, so this is our first example. And I don't know if you guys remember what we found there, but that value was 64/3. So this is how you're going to know, oh, I'm trying to find the area under the curve. You're going to see the integral symbol, but it's going to have bounds. So we call this a definite integral. So I am going to apologize on behalf of mathematicians right now that we're using the same symbol that you use for antiderivatives to do a completely different thing. Thanks a lot, mathematicians. Right, okay, so, but realize it's not exactly the same. There is a difference. We have numbers on this now. And as soon as there are numbers on it, it means do something different. Okay, so this is the symbolism. This is how we do definite integrals. Okay, so let me give you some properties of definite integrals. These are just some things that are going to be useful in the future. And then we'll talk a little bit about what happens if the function's actually negative and all that. All right, so here are some properties of the definite integral.
I have a question real fast about that. So I feel like at the end of our class, I had Larry last quarter. We learned like a different way to solve it because we did have like a couple problems with the numbers. So could you do it that way too? I don't remember exactly how. It's been too long, but
Okay, I think what you're thinking about is the fundamental theorem of calculus, and we're going to hit that, I believe, on Monday.
okay.
Okay, so check with me. After Monday, or after we do fundamental theorem of calculus, whenever that happens, Alexi, let me know if I answered your question, or if that was what you were thinking about, or if it's something different. Because if it's something different, I'll try to figure that out and let you know. But I think I'm going to guess what you're thinking is what's called the fundamental theorem of calculus. So just let me know on Monday if I don't catch your, if you still have a question. Cool. All right, so definite integrals. Here are some properties. All right, so here's the first one. Let's say we're going to have a definite integral where the bounds are the same. Okay, where these are both the same. So this would be from 3 to 3, from 10 to 10, from -2 to -2. All right, if your bounds are ever the same, no matter what the function is, you're going to get 0. And this should make sense. Can you see why that has to be 0?
Because there is no interval.
Yeah, there's no, like, we're looking at, remember what this is telling us? This is telling us where to search for the area under this function. Well, what's the area under a function from one point to that same point? Well, there is no area, right? At best, it's a line, so it's got no area. So that's exactly it, is that this basically means that there's no interval. So if there's no interval, yeah, of course we're going to get 0 when we do this. Okay, so there's your first property. Yay. Now, this next one is a little bit weird. But this one is, what if we were to change the bounds on that integral? So instead of going from smaller to bigger, we go from bigger to smaller. Now, this one, I'm just going to tell you what that equals. But basically, this says that if you were to do it the other way, so instead of going from 2 to 5, we think of it as going from 5 to 2, we're actually going to get the opposite sign. All right, so think about that one that we just did, the x cubed minus 1 from 2 to 5. Gave us a number of 75 halves. If we went backwards, if we said we're going to integrate from 5 to 2, the answer would actually be negative 75 halves. All right, now this one's a little bit harder to see geometrically because to us, area is area. Area is a positive number and all that. But this is really the same sort of thing that's happened to you forever in math. Like, what does a negative actually mean? If you go back to what does that actually mean? Like, what's the difference between 5 and negative 5? Well, it's just direction. 5 is 5 steps that way from 0. Negative 5 is 5 steps this way from 0. So negatives actually only mean going the opposite way. And you see that all over the place. Think about derivatives. Positive derivative versus negative derivative. Positive means we're going up. Negative means we're going down. Right? So we see this sort of thing all the time. Well, that's all this is. If instead we go the opposite direction, and we think about this as going from right to left instead of left to right, we're going to get the negative. We're going to get the opposite value. This will matter later. Right now, in terms of how we're talking about areas, it doesn't really make sense, but it'll matter later. But there's a second property of your definite integral. The next two, well, actually the next three, I guess, they all come from properties of sums. So the third one here is, what if we're integrating from A to B, but we have a sum or difference of functions. So we're going to add two functions or we're going to subtract two functions. Well, it turns out that with integrals, you can actually split it up into the two different pieces and do them separately. So we saw that same property with sums, and the reason that this works is that these are just sums, right? Definite integrals are sums that we take a limit on, but we know that both sum and limits allow us to do this, right? Split things apart. All right, so we got that property. We also have a property that says, what if we have a constant multiplier on here? Well, you guys know what we're going to be able to do. We're going to be able to pull that thing out. We can pull it out of sums. We can pull it out of limits. Well, constant multiples we can pull out of definite integrals. So, you know, if you go back and you look at the properties for limits and the properties for sums, all of those properties are properties of integrals, because that's all integrals are. They're limits of sum. Okay, so basically this is just going to let us break things apart and do them individually, because sometimes it's faster to do them individually. And it's definitely way easier to pull constants out, so we can just take care of those at the end. All right, now the last one is a little bit weird. But let's say that there is some place, I'm going to call it, well, we'll call it C. And I don't know if you guys have seen this symbol. Those of you who took Calc 1 with me definitely saw this symbol. Depending upon who else you took it with, you may not have seen this, but this thing means contained in. It's like a little, like a curvy E or a C with a dash through it. But this is C is contained in AB, meaning it's some point that's somewhere in that interval. All right, so basically, if we were to draw this, here's A, here's B. C is just some number that's somewhere inside. Okay, so that's all that means. All right, so if C is in the interval, then what we can do is if you have an integral from A to B, you can break it up into two intervals. Get out of the way there. All right, but what this says is you can take an interval and split it however you want. You can find any point in there and use it to cut it into two pieces. And this should make sense, especially from an area kind of argument. Here's what this means in terms of area. So here's our shape. Here's A, here's B. What this is saying is you choose somewhere in the middle, C. We can actually think of that total area as the sum of these two areas. The blue one, this is the integral from A to C. The orange one is the integral from C to B. So this is a picture of what's going on there geometrically. We're just splitting it into two chunks. So this is also very useful. You'll see in lots of situations. Basically, just split it wherever you want it. Now, the first consequence of this that I want to definitely mention right now is that this makes it so that if you want to calculate an integral, you don't necessarily have to have a continuous function. You can have discontinuities as long as you can split it into a bunch of regions that are continuous. So this takes care of discontinuities like jumps. Remember those discontinuities where like you're coming in from different sides and you get different limits? No problem. Break it up right there into those smaller integrals and we can do it. It also takes care of the ones where there are holes, right? The removable discontinuities. It doesn't help with infinite discontinuities. Those we're going to have to tackle later. But this is kind of nice. It actually makes it so that you don't have to have a continuous function. It just has to be what we call piecewise continuous. You have to be able to break it into a bunch of continuous chunks. All right, let me give you a couple of more properties and then we'll call it a day. So here's another one. That was number 5, right? I think we're on number 6. If not, we're on number 6 now. So let's say that we know that f of x is greater than or equal to g of x. So f is just bigger than g. Then what we know is that the integral of f of x is going to be greater than or equal to the integral of g of x. And again, this should make sense. Think of it as an area idea. If f is taller than g, there's more area under f than there is under g. That's what this is saying. Okay, cool. And then we also have this. What if f of x is bounded? Okay, so what if our function is trapped between two numbers? This is a lowercase m, this is a capital M. All right, so this just says that our function is trapped between two values. Well, then what we know about this is that the integral of f of x is also going to be bounded and it's going to be somewhere between the two numbers, little m times b minus a and big M times b minus a. All right, now this one, just looking at it, may not make sense. You might go, what the, where's the b minus a coming from and all that? But if you look at it graphically, we draw a picture, it's going to make total sense. So let me draw a picture here of a function that's bounded. All right, so here's a, here's b, and here is our function. So in the context of little m and big M, there's little m and there's capital M. Right, this function is smallest value is little m, its biggest value is big M. Now I'm going to draw these three things as areas so you can see what's going on. Now the area under the curve, you know that one. That's this, right? So there's our integral. Let's look at this left-hand side. It's m, little m, times b minus a. Well, little m times b minus a is the area of this rectangle, right? Height times width. Big M times b minus a is also the area of a rectangle, but it's a rectangle with height big M. All right, so graphically, here's your graphical proof of this statement. So hopefully you can kind of see what's going on. The area under that curve is going to be bigger than the rectangle that's formed by the lowest value. And it's going to be less than the rectangle formed by the highest value. So when a function is bounded, we actually have also bounds on the integral. There is a maximum and a minimum value. So if you want to just make a guess and say, okay, what is the actual value of this? You know a top number and a bottom number. You can refine it better, obviously, if you know that function, you can do the sum formula and all that. But we definitely are going to have bounds on an integral if we have bounds on the function. Okay, so lots of properties, lots of things that all come from just areas and sums, and because that's what we're doing. Now, we still have to address the what if a function's negative? Because, you know, so we haven't even gone there yet. So we'll actually start with that on Monday, obviously after we talk about homework questions and all that. We'll start with the, okay, what if it's negative? What's going on if the function is negative? And then we'll get to the, right, but there's got to be a faster way. Because trying to do that limit and sum stuff, ugh, I mean, it sucks, right? I mean, there's a lot of stuff in there, a lot of algebra, lots of places you can make mistakes. There's got to be a faster way, and there is. There is, just like there was with derivatives, right? Like we define derivatives, slope of the secant line, then we do the limit, but then we learned the quick way. We learned those rules. Well, we'll do the same thing here. We'll develop rules for definite integrals. Because why do it the long, hard way every time? All right, so that's where we're going. That's what's going to happen on Monday. So with that, I'm going to go ahead and stop our recording, and we'll call it a day.